other words, this part has to be true.
And that's how you prove it?
Hmm?
And that's all the steps it takes to prove
Yep,
it?
this is proof by contradiction. Now, since you guys won't be asked to prove anything like that in this class, the next time you'll be asked to prove something in the computer science class will be CISP 440. It's called discrete structure. It's actually more about math than it is about programming. But are we okay with this proof? Intuitively. Okay, this is not a math class. I just want to give you guys some exposure of how to prove something. But this proof is only here because I want to make sure that I can optimize my algorithm without making it incorrect. Okay? So what is the significance of this particular theorem in terms of my algorithm to find a prime factor of a particular number n? Remember this example here, 6571 is a prime number. Okay? We know now that it is a prime number. But when you're testing it in your program, you don't know it's a prime number. So the question is, when do you get out of the loop and conclude, okay, I don't need to go any further because this is a prime number, the only factor is itself. So according to this theorem, what can we do to make our algorithm go faster? We'll still have to test 2, 3, 4, 5, 6, and so on. But this has to do with when we can get out. Because by the time we get to the square root and we cannot find a factor, what do we know for sure? There will be no factors, right? There will be no factors other than itself, because according to this, if the number itself is a composite, then one of the factors has to be less than the square root of the number, which also means that by the time I exceed the square root of the number, I still cannot find a factor. There's no factor. Okay, very good. So now we're making the connection. So the next step is to make use of that theorem, make use of tax finding to optimize the algorithm. We still want to try with 2. Okay, 2 is still the first prime factor we want to use to try something. Inside the loop, we still have the same condition as before, which is n mod f does not equal to 0, because when n mod f does equal to 0, f is a factor of n, and I should get out. But if I want to get out in the case that n is a prime number, I have to use a conjunction and say, if I want to stay in the loop, I want some additional condition to be true to stay in the loop. And that condition is f times f has to be less than n. I'm making use of the theorem in this case. The body of the loop is still the same. Just move on to the next one while both conditions, as long as both conditions are true. Okay? But when we get out, there's one more thing we need to do. Because if you think about this, it will get out when n is a prime number and f times f is greater than n itself. But what is the purpose of this algorithm? Is the purpose of this algorithm determining whether n is prime, or is the purpose of the algorithm finding a prime factor f of n? It's finding a prime factor f of n, right? So when n is prime, this algorithm is no longer giving me a prime factor f of n, because it's just giving me an f that is more than the square root of n, which is not a factor of n. So that means there's one more thing we need to do at the end of this algorithm. We need to say if f times f is greater than n, then the prime factor is n itself. Because when f times f is greater than n, it implies that we exited the algorithm earlier because f times f is greater than n, and as a result of that, we have the conclusion that n is prime. When n is prime, then the prime factor of n is n itself. Without the conditional statement, it will still exit at the right time, but it won't give me the correct answer, because the answer is f has to be a prime factor of n. Okay? Any questions about why we have the conditional statement after the loop in this case? What about the case when f times f equals n? I mean, I did not specify f times f equals n here. I did not specify f times f equals n here. What does it mean when f times f equals n? That means f is a factor of n, right? So that means I don't have to check for that in the conditional statement, because if f times f does equal to n, it would have made the first condition false to begin with. It would not get to the second part anyway. And I definitely should not specify greater than or equal to here, because if f times f equals n, then f is a factor of n, and n is not a prime number. So that's why, in the condition of the conditional statement, we don't specify greater than or equal to. We only want to specify greater than. This optimization is going to be more important than using only prime numbers. Okay, this will speed up the algorithm significantly, more so than only using prime numbers, for f. Are there any questions at this point? No questions? Okay. If there are no questions, we are done with the top-down design slide. I'll just go back and double check and make sure that we did cover everything. I think there are some topics at the very end that I have not covered yet. So we'll go back and talk about that. Okay. So top-down design isn't everything. That's basically, saying, but why are we, reading this chapter if top-down design isn't everything? Well, top-down design isn't everything because there are certain cases where you cannot do top-down design all the time. One approach of writing programs is called bottom-up. Bottom-up is trying to figure out what is the most basic and the lowest level of operation for this type for a particular type of program. You finish the most basic operations first, and then you build upon of those most basic operations. Basically a second layer, and then you add a third layer, and then you add a fourth layer, and so on. Bottom-up design usually works when you are trying to come up with library subroutines. In other words, you're not writing a program to begin with. You're writing utilities, okay? Subroutines that other people may need to rely on. Okay? And in those cases, bottom-up design actually works fairly well. It also works extremely well when you are designing something that has a hardware component to it. Like when you're designing drivers, device drivers, or anything that has to operate on a particular piece of hardware, then bottom-up design works really well, because in that case, you start with a schematic diagram of your circuit, and then you work from the circuit up to the first layer of software, and then you work your way up in those cases. With your typical homework assignment in the college, bottom-up design usually does not work as well. Okay, so you should still use top-down design whenever possible. Occasionally, you would write a program and start writing it and modifying it, adding stuff to it, and before you know, you have a 200-line subroutine. When you have a subroutine that is too long and you can no longer keep track of the program itself, what do? You use abstraction. Okay? What abstraction means is you take a chunk of code from your subroutine or your algorithm, and you say, oh, collectively, these 20 lines is doing this particular task. So what you do is you take that 20 lines out of your algorithm and replace those 20 lines with a single statement saying that, okay, replace it with a single statement saying what needs to be done, but not how it is done. So the how it is done part is left in the definition of the subroutine itself. So we'll see more of this when we talk about subroutines. But abstraction is one way to turn a messy, long, big subroutine into a more structured, hierarchy of subroutines. Any questions about this? Okay. If there are no questions about these, we can now move on to the next module. The next module is very exciting because it talks about arrays. Arrays are truly different. When we talk about top-down design, we are mostly talking about how do you design a program, the approach of writing programs. But we did not introduce any new additional programming language elements or concepts. When we move on to arrays, this is interesting because it allows us to write algorithms that we could not previously. So we'll go ahead and take a look at arrays now. But before we talk about arrays, let's go ahead and go back to some of the pseudocode that we have seen over and over again before, and then we try to ask the question: can we extend this type of algorithm to handle this many variables? So we'll start with this one. If x is greater than y, then z gets x, else z gets y, and if. Do you still remember this algorithm? One of the very first that we talked about. What does it do? It finds the maximum of two variables, x and y, and make z the maximum of those two. Can we find the maximum of three variables? Yeah, we can do that. Okay, so this one finds the maximum of two variables. To find three is not that big of a deal. We can just say if w is greater than or equal to x, and w is greater than or equal to y, then z gets w. Else if x is greater than or equal to w, and x is greater than or equal to y, then z gets x. Else, since w and x are not the maximum, the only thing left is y, and if. Do you still remember that? Okay, the logic to find the maximum of three variables. Using this, can you write an algorithm that will find the maximum of four variables? Sure, it's not too big of a jump. Just say if v is greater than or equal to w, and v is greater than or equal to x, and v is greater than or equal to y, then v is the maximum. Given an assignment statement, and so on. Can you extend it to five variables? Sure. How about 30,000 variables? Sure. Except those lines will be kind of long, right? Because every condition will have 30,000 minus 129,999 comparisons, and you will end up with 30,000 branches, right? But it's still doable. You can probably write a program like that. It will take a long time to type that program. And the other part is, what if you have a little typo somewhere in the program? Instead of greater than or equal to, you use a greater than where it is not expected. Then your program has a bug. But that bug will not be easily found because it will only happen when in certain types of combinations. And the worst part of that is, what if your boss, being me, tell you that, guess what? Your program now has to handle 30,001 variables. How much do you have to change? Every other line, right? And you have to add 2 more lines. Okay? So it's not a very scalable approach to solve problems, to find the maximum of a bunch of variables. Let me show you what arrays can do. Okay? Arrays make this type of algorithms scalable. If I want to do this using an array, I would do something like this. Don't ask me what the symbols represent at this point, because I will explain that later. And then you can say if z is less than a bracket I, then z gets a bracket I, and if I gets I plus 1, and y. Okay. I know I have not explained the square bracket, what it does. I have not explained the